Hello, intro to stats students. Today we are going to start chapter 7, chance and probability. It has two sections, section 7.1 and 7.2. And today we're starting section 7.51, thinking about chance. Alright, so let's move to the very first part. Here we're talking about idea of probability. So the core concept here, the core basic idea is that the chance behavior is unpredictable in short run but has a regular and predictable pattern in the long run. So what does it mean? Here you have to keep in mind they're talking about short run and long run. It means whenever you're doing some experiment or something is chosen any kind of event, the chance behavior is always uh, unpredictable when it is in the short run. Here, when this is in short run, not in a and in a long run, you can predict it. When you're just doing one or two, three trials, you can predict. There is a randomness. There is uncertainty. But when you're conducting something, some experiment, when you repeat it several times, long run, then you can have a predictable pattern over there. So this is basically like when we and why we do it, when why we use it, uh, or where we use it. We use it basically like whenever there is a football game and we just toss a coin because we don't know that for particular trial what's the outcome going to be, whether it's going to be head or tail, or so that avoids favoritism, that simply not puts any kind of bias in the result. So like for survey or the clinical trial, or if you're doing some kind of sample survey, if you're allotting a patients to the treatment of placebo groups or medical experiments, a clinical trial, so or other area or some kind of games. So this kind of event where you have to choose something, you have so randomness is very important in order to avoid the favoritism. And basically in this book we have talked about random samples and randomized experiments. Is almost this, it is the same thing because that is avoiding the favoritism and giving an uncertain result in a short run, but we get a predictable behavior pattern in the long run. So like when you toss a coin, in that case, um, what happened, if a simple random sample, if I'm tossing a coin, my first trial, can I be very sure I'm going to get head or tail? No, I can't be. So it can be predicted, it can be. But if someone says, okay, I'm going to toss it for 1,000 times, what's the probability, how many, what's the chance I would get tail and head? So then you can simply generalize it is going to be half or 0.5. So in a long run, so that's the context I was talking about, long run and short run here. So is basically when you just uh, toss it once, first and second time, you can predict, but when you repeat the several trials, then you are able to understand what it is. So let's move to the next page. So in next page we are going to start the coin tossing. So here in coin tossing, what we're supposed to know, that this is basically a graph here. This is a graph given here, and what they want you to show, that if you just toss a coin first time, if it is your first trial, and you may get if they're talking about, if it is a uh, if you're talking about heads or tail, all right, and if you toss it just one time and if you toss it 1,000 times, so they're just trying to figure out a certain behavior of the results. But when we toss a coin, so coin toss, there are just two two options, either you get heads or you get tail. All right, they're just two options, you get either head or tail. So if you're doing your first trial, and when you do your first trial, this is your trial, and when you have a first trial and you get one head, so if you have head and tail, you just get one head. So in that case, out of one, how much you so it is out of one uh, trial you have one head. So what's the so here proportion, if you're trying to find the proportion, that is 1. So your proportion is 1 here, you just put it here, and that's a graph here where it shows different values. Now what if I'm going to toss it second time? If I'm going to toss it second time, my second trial, here my second trial, and now it is a tail. Now it is a tail. You can see here I'm just using the same column. Now this time it's a tail, it's 1. So now total, how many trials you have done? You have done total 2 trials. Out of 2 trials, and you're just finding, because here your this graph is number of tosses, but here keep in mind this is basically about proportion of heads and number of tosses. It's finding the relation between these two. So proportion of head, in this case, how many heads you have up to second trial? You have just one head, so it's 1/2, that's going to be 0.5. Alright, so let me write down 0.5 here. That's 0.5. So you can see it is here, it is pointed here. Now let's move to our third, next 3 tosses. They say if you do next 3 tosses, 3, 4, 5. So next 3 tosses gave a tail followed by 2 heads. So what you have got, you got a tail, then you got a head, and then you again got a head. So or let me make it head and tail like this, that's better to see or visualize. So if we have total 5 trial, so up to here from first trial to 5th trial, total how many trials we have? We have 5 trials, and we are just doing it for the proportion of heads. So how many heads we have? 1, 2, 3 heads, so that's 3/5. And 3/5 is what it's given here, that's 0.6. So for that, our next point is going to be 0.6 here when it is after 5 trials. So 5 trial, you can see it is here 0.6. Alright, so same way, if you keep on increasing many times, and you can see that the final value of the proportion gets very close to 0.5. all right, so that's why, so the graph here, it keeps on getting very closer to the middle line, where, and what it is, it's actually 0.5. It's getting very close to 0.5. So because as it's in the long run means you're increasing the number of trials, and it was the short run where you just can't predict what it is going to, but in long run you can predict it's going to be 0.5. the proportion is going to be 0.5. So we can finally say the probability of heads is 1/2, and vice versa, you can say probability of tail is also 1/2. So on this page they basically say that randomness, or random even in a statistic, is basically, it's a haphazard kind of event where it is not, in a short run it is not predictable, but when you do a long run, then you can easily predict what's the outcome going to be. So let's move to the next part. So there can be a confusion here, that if we have if you're tossing a coin, the probability is going to be 0.5. So we may think, oh, it has two sides, or that's why it is having 0.5 as a probability. So but let's take another example. If we're talking about the sexes of babies, so we'd see that the probabilities were not equal. And how we got this probability, it's basically, this is based on the data, based on the data rather than theorizing. So theorizing was on the we theoretically we say that is 0.5 when we toss a coin, but actually experimental probability here, or based on the data, when we collected the data from many birth of the babies, then it was nearly 0.51, not 0.5. So actually we can theorize it, or we can say it with more confidence when we increase the number of trials. And that's very important to have a definite outcome for any experiment or trial, until unless it is, so we should be doing it many times. So there is another example of coin tosser. So example 7.2 here, it talks about basically three examples where a French naturalist, Count Buffon, um, he tossed the coin for 4,040 times. And what was the result? Result was 2048 heads. So the proportion was 2048 out of 440 4040 trials. So and total, the answer was, the probability is 0.5069 for heads. Same way, another statistician, Carl Pearson, he also did a coin tossing experiment where the total number of tosses were 24,000, but the results were 12,012 heads. So proportion is going to be what? In that case, the proportion is going to be it's going to be 12,012 divided by 24,000, and your answer is going to be 0.5005. That's the proportion. Same way, another mathematician during World War II, South African mathematician John, he tossed it 10,000 times, sorry, and he got 5,067 heads. And in his case, the proportion was 5,067 heads out of 10,000 trials, and the answer was 0.5067. So you can see all three people, the first proportion is 0.5069, then 0.5005, and then 0.5067. All three are very close to each other but not exactly same. So this is kind of experimental probability. Let's move to the next part. So here we are going to just summarize two important concepts: randomness and probability. For randomness is basically, it's a phenomena that any outcome for some experiment or some trial, the value or the proportion or the probability for a short term, it's not going to be certain, it's uncertain. But when it is you're doing a large number of trials, or you're repeating it many times, then in that case you can see a regular distribution of the outcomes. You can see a certain pattern over there. You can then have a theoretical probability of some certain event. Now what is probability here? For probability of any outcome, keep in mind the value of probability, it can always take between 0, it can always take values between 0 and 1. And actually what it is the proportion of times the outcome would occur. So it is basically, if we are checking the probability of heads, how many times the heads will occur in certain number of trials, so that will occur between 0 and 1. But when we are uh, when we are talking about the probability, the zero never occurs, because in a long run, uh, you don't see even in a short run when you're doing it with probability 1. If you do a first repetition, first time you get your head, and as we discussed in our previous graph, then when you did the second trial, it was 1 out of 2 trials, so half of the trials. So we can never observe it exactly what it is. So mm, it is ideally we cannot calculate it for certain event, but yes, we can always generalize it whenever we do a long term, long term or different many trials. Then we can have a certain uh, outcome for that. So probability just gives us a language to describe the long term regularity of random behavior. So let's move to the next page. So for this long term and short term, the pattern of the probability where we can talk about some general behavior. There is an example of life insurance. In example 7.3, the probability of dying. What happens the people when they have life insurance? So the insurance people, they the National Center of Health Statistic, it says that the proportion of aged men 20 to 24 who die 1 year in any 1 year is this. And the same thing, the probability for the young man will die, yes, that the next year. And this is the probability for the young man dying between 20 to 24, that age. So that's a proportion here. And for the women, they have the proportion 0.0005 uh, for the next year. Within a year, they saw that between 20 to 24 aged um, young men and women, this proportion died for men, and this is for the women. So when they have this pattern, they saw that when they calculated the probability for young people aged 20 to 24, they saw that about they converted this number into probability. So they have 0.15%, and the same way they converted this number into probability, they multiplied by 100. For women it is 0.05%. So they said that yes, they have to pay more to the men because they're dying more in compared to women. So it will be, it will be uh, more money for them to pay. So what they did, they started charging more for insurance to men because they have more chances of dying. So because they have to pay more for them. So let's move to the next part. Now they talk about ancient history of chance, like in past, in ancient time, how do you they used to use this chance thing. There they used to do different games of chance, where they used to roll a dice, a shuffle card. They used to use a spinning a roulette wheel. So these were the few things they used to use for chance, or to select something, or for different purposes. And they thought, they remotely, they just thought it's the will of God. Whatever the will of God, it will be there. So but the very most common method in ancient time was the rolling the bones. What they used to do, tossing several struggly, they used to toss that. And it was a struggly was what it was, basically a solid, quite regular bone from heel of the animals. So it's a heel of the animal. You can see the heel has, it has 4 sides, and whenever they used to throw, then it will come to the rest as at one of the sides. So you can see that's one side here, one side here, second, and the remaining two are in the back. You can imagine they are in the back. Same way, so this is the sheep's one and this is the dog's one. So that way they used to throw it away and roll it, and then whatever the side they get, they choose accordingly. So this is the animal heel bones struggly actual size, and it is basically used to do the games or other kind of selection procedure. So let's move to the next part. So the clinical, so the devices, like in ancient times they used to chance device a struggle, they used to do the selection or some kind of experiment or some kind of games they, if they used to do. So what happened over there, because the device was not that fair, it is made of it was not a very regular pattern, it was many throws of bones and dice. Um, it was different kinds of bones and dice, so where the outcome was not that fair because irregular shape, and each time it had different pattern of outcomes. So that they never thought about in the back, but usually the professional gamblers, they used to think about that there is certain pattern when they use the dice or cards, try to, and they used to adjust their bet accordingly. Even in the past, the French gamblers, they asked French mathematicians for help in figuring out fair value of bets, so how they can win, what kind of bet they should make. So probability theory is basically finally originated is the study of randomness. Probability theory is the study of a mathematical study of randomness, and originated by the Pere de Fermat and Blaise Pascal in 17th century, and it is studied till now. I hope you get it, and I'll do the next section, and stay safe. Thank you so much.